Today, we're going to journey deep inside one of the most familiar particles in the universe, the proton. And I promise you, what we're going to find in there is going to completely change the way you think about it. It's truly mind-bending stuff.
So, let me ask you, what's inside a proton? If you immediately thought 3 quarks, well, you're not wrong, but you're also not really right either. The truth is so much weirder, so much more chaotic. It's this shimmering, bustling sea of particles, and we're going to dive right in.
Okay, so let's start with the basics. We've got to begin with that simple picture most of us learned in school, the classic textbook proton.
In this super simple model, you just imagine these 3 little guys, called valence quarks. 2 are up quarks, 1 is a down quark. And the key thing here in this naive picture is that they're not interacting at all. They're just kind of hanging out in there together.
Now, if they're not interacting and they're basically equal partners in this whole proton deal, it just makes sense, right? They'd split the proton's momentum 3 ways, perfectly even. So if you could measure one of them, you'd expect to find it carrying exactly 1/3 of the total momentum.
And here's what that would look like on a graph. See that horizontal axis, x? That's just the fraction of the proton's momentum a quark has. And that dotted line? It's a perfect, sharp spike right at 1/3. It's a clean, predictable picture, and it's completely wrong.
So, all right, let's add our first dose of reality. We know these quarks aren't just floating around. Something has to be holding them together, right? There's a force at play. And the source material for this explainer gives us this fantastic analogy. You can think of this force like a set of invisible rubber bands that are stretching between the 3 quarks, constantly pulling them together.
So what do these rubber bands do to our measurement? Well, things get a little wobbly. Instead of that sharp spike, you get a range of possibilities. Sometimes a quark has a bit more momentum, sometimes a little less. But if you averaged it all out, it would still be centered right at that 1/3 mark.
And you can see exactly how that changes our graph. There's our original perfect dotted line, and now look at this new dashed line. See how it's smeared out into a nice curve? That's our rubber bands at work. It's a much more realistic picture, but believe me, it is still not the whole story. Not even close.
All right, now we get to the really good part. To see what's actually going on inside a proton, we have to unleash the full, bizarre, wonderful power of quantum chromodynamics, or QCD for short.
And here is the absolute game-changing question. What happens when these quarks aren't just sitting there, but are constantly taking part in a wild quantum dance? What happens when they can emit and then reabsorb other particles?
Well, when they do that, they create what physicists call C-partons. Just try to picture this, a chaotic, frantic swarm of virtual particles. You've got quarks, you've got their antimatter twins, the antiquarks, and you've got gluons, the particles that carry the strong force. And they are all constantly flashing into existence out of pure energy and then vanishing an instant later.
So this is the crucial thing to get. The 3 valence quarks, they're the permanent residents. They're what make a proton a proton. But the C quarks and gluons, they're like fleeting visitors, just quantum fluctuations that are constantly popping in and out. They don't change the proton's identity, but they totally transform its internal environment.
And now, the real picture. That solid line is what we actually see in experiments. And just look at it. Way over on the left, at really low momentum, you see this enormous towering spike. That's it. That's the quantum sea. It's this huge, churning crowd of low-energy particles that absolutely dominates the inside of the proton. So, forget that idea of a quiet little home with 3 quarks. The proton is a chaotic, bustling metropolis of particles popping in and out of existence all the time. It is so much more crowded and dynamic than we ever thought. Now, discovering this quantum sea has some really profound and honestly super strange consequences for how we think about these particles, especially for our original 3 valence quarks.
I mean, think about it for a second. To create this whole sea of particles out of nothing, where does the energy come from? It has to come from somewhere. It's borrowed from the valence quarks. Every time a valence quark spits out a gluon, it loses a little bit of its own energy, a little bit of its momentum.
And the effect of this is huge. Remember how our peak momentum used to be at 1/3, or about 0.33? Well, in reality, the most likely momentum for a valence quark isn't 1/3 at all. It's been shoved all the way down to about 0.1. That quantum sea just eats up a huge chunk of the available energy. This whole idea leads to a phenomenon with a kind of funny name, scaling violation. But the concept behind it is incredible. It basically means that what a proton looks like on the inside isn't fixed.
What you see literally depends on how hard you look.
Let me break it down. So imagine you poke a proton very gently with a low-energy probe. Your vision is blurry, you can't see the fine details, and at that low resolution, it pretty much just looks like 3 quarks. But if you smack it really hard with a high-energy probe, your resolution gets way better, and suddenly you can see all those tiny fleeting C-partons. The proton reveals more of itself the harder you look at it. How wild is that?
So, after all of this, we have to ask a really fundamental question. What even is a proton?
Well, for starters, we know it's not just 3 quarks, not by a long shot. It's this incredibly dynamic, ever-changing system. It's got the 3 permanent valence quarks, sure, but they're swimming in a roiling sea of gluons and virtual particles. And maybe the most important thing is that its very contents are relative to us, the observers.
And that leaves us with one last big thought to chew on. If a particle that we call a fundamental building block of matter can literally change its appearance based on how we look at it, what does that say about our whole idea of a fundamental particle? It really suggests that at the deepest levels of reality, things are far more fluid, far more interconnected than we ever dared to imagine.